Thank you very much. So, good afternoon. My name is Kunshi, and I'm a PhD student from China and in Zhejiang University. And today, it's my great pleasure to share my work, radar and camera fusion for multitask sensing in autonomous driving. So, my presentation will include the 4 parts. The first is a research background. So nowadays we know that there are more and more autonomous driving cars in the road, and recent years have witnessed the faster development of computer vision technologies. However, the effectiveness of the image-based object detection is still limited in adverse conditions, such as heavy fog, the lens flare, and the poor illumination. Therefore, we consider to utilize camera and radar fusion. For camera, it has rich textual information, but it is weak in adverse weather or dim illumination. For radar, it has all-weather workability, as shown in this table, but it suffers from the sparsity of radar points and is poor in object classification. So we want to explore the camera and the radar fusion to exploit the mutual synergy. So for the multi-modal fusion, there are 3 main components. The first is what to fuse, the second is when to fuse, and the third one is how to fuse. For the what to fuse, it means the data representation, and for radar, we consider the sparse point cloud. So for the camera, we use the RGB image. The second one is when to fuse. It means at which stage the fuse operation is conducted. And it can be divided into 3 types, meaning the data level fusion, the future level fusion, and the decision level fusion. Our work is focused on the future level fusion because it's related to the deep learning. And the third one is how to fuse. It means a concrete fusion operation. As we can see in this figure, the typical fusion operation is element-wise add and the concatenation, but it's too simple, so we devise an attention mechanism to conduct the fusion operation. This table is about the public radar datasets. The most famous datasets in autonomous driving, which containing the radar data, is the nuScenes dataset. The first line, it was published in the CVPR, and it contains radar, camera, and LiDAR, these modalities. For the radar data, it contains a 2D sparse point cloud, and this dataset is very big, and the label is 3D boxes. And this table is about the radar work in multi-modal fusion. There are many works, but this table only concludes the most famous one. As we can see that most of the paper I selected is about radar and camera fusion, and the fusion level is usually the future level, and most of the work utilize the projection methods, which means that the paper usually projects the radar data, which is a 3D, to the camera plane, which is 2D. And the fusion method is simply the concatenation or the element was add. So we conclude there are also very defects of the existing methods. And the existing methods is divided into 3 types. The first type is a projection-based fusion, which means it conducted the radar to camera projection, and it struggles to distinguish the occluded objects, because in the front view, the occluded objects is nearby to each other. And it exaggerates the sparsity of the radar data because in the original data, it is 3D. When it is projected into the 2D image plane, it will be more sparse. And the most problem is that it is sensitive to spatial temporal collaboration. So we don't use these methods. For the second one is ROI-based fusion, and it leverages one modality to generate range of interests. And then this ROI contains valid objects. But it may cause some misdetections. And the third one is to integrate view fusion. And it first extracts and integrates the proto-wires features. In this method, it usually represents radar point cloud in a voxel grid, but the grid representation of radar data is inefficient when the radar points are sparse. Since we use the nuScenes dataset, as I mentioned before, it contains the sparse radar points. So this method we also didn't consider. So we used the second method. Next is the proposed methods. So left, the picture shows the nuScenes dataset. You can see that this is the camera radar coordinates, and the radar is very sparse when it projects to the image. So there are three main problems about the radar data representation. The first is sparsity, and the second is height missing, and the third one is clutter, which means noise. So for the sparsity, we accumulate the multiple radar swaps based on full velocity complexity, which means that we accumulate the multi-frames of the radar points to generate more dense points. And for the height missing, we transfer the radar points to 3D pairs, which means we expand the 2D point to a 3D pairs, and the height is determined by the distance. And the third one is clutter. It is most problem in radar processing. So we utilize frustum-based radar camera association, which means that we first utilize camera data to detect the 2D and the 3D bounding boxes and the depths. Then we use this information to formulate this frustum, and only we use the radar point inside this frustum so we can filter some noise. And this is overall model architecture. For the radar point, I have cleaned. And for the camera data processing, we employ a center-based network like this, and to generate image features and predict the 2D and the 3D object bounding boxes, etc. And for the depths, we conduct a radar and camera pixel depth association technique to estimate more accurate object depths. For the full velocity, we leverage optical flow from a camera radar pair to calculate full velocity. And for fusion, we conduct a frustum-based radar camera association, as I mentioned before, and then fuse the two modules with an adaptive two-stage attention module to explore the synergy of the features. Finally, the integrated features are sent to the second regulation heads. So next, I would like to introduce this attention mechanism. It is about the fusion operation. This two-stage attention module is aimed to discard some unnecessary information and retain the significant features. Just as this figure shows, this contains two stages. The stage one is intra-sensor self-attention, which means this green part. And the second one is a stage 2 inter-sensor cross-attention, which is showing orange parts. After this attention mechanism, we can achieve the complementary interactions among the radar and the camera sensors. Next is the experiments and the results. So for the data set, we use this nuScenes data set. It is a very, very famous data set in autonomous driving. And the sensors equipped in the collecting cars contain 5 radar and 6 camera. And it contains 1,000 scenes. For training, we train the model for 60 epochs with a batch size of 26 based on deep learning. And next, I would like to show some quantitative results. The methods we used is this, and the center net is the camera-only method, and center fusion is the sorter camera and the radar fusion methods. We utilize the nuScenes dataset metrics, include the box location, which is the size, the rotation, the velocity, and the attributes. Let me explain the meaning of these metrics. The first one, ATE, which is related to the translation. It means the central distance in the 2D. That is a detection box and the ground truth. The second one is the scale error. It means the 3D IOU after aligning, orientation, and translation. And the third one is orientation. It's very it's simple, so I didn't explain. The first one is the velocity. It's also very simple. And the fifth one is attributes, which means maybe the people is walking or it's standing. This is the attributes meaning. And the overall metric is this nuScenes detection score, NDS, which is average of all these error metric and the MAP metric, which is very common in the deep learning. So we can see that our methods outperform the camera-only center net and the center fusion in terms of all metrics, especially in this velocity metric. And the improved depth estimation and the fusion module are conducive to raising the detection scores. Finally, there are some qualitative results. We can see that the upper line is center fusion, and the lower line is our method. In this figure, the red box represents the ground truth, and the blue box means the predictions. The green point is the radar points. So we can see that our method is more accurate for object detection, and it achieves fewer missed detections and achieves fewer false alarms, and it can obtain more accurate velocity estimation. So to summarize, we addressed the 3 principal problems in the utilization of radar point clouds, and we proposed a novel radar camera fusion framework, and we integrated a 2-state attention module, which combines the self-attention and the cross-attention. In future, we will proceed to explore the transformer-based methods for the radar and camera fusion. As in the NLP domain, the transformer has achieved very great performance, and we will leverage the transformer structure as a substitute for the manually designed alignment operations. And this is a reference in my paper. Thank you, many thanks for your attention.